So 2 tasks today. First one is to introduce SPI. Another one is introduce the course project. Really quick. So first, SPI is communication protocol. It's a digital block. If you look at because for the IPGA class, we are writing every single detail about the bottom level circuits, right? So if you look at the Verilog code, you will be able to understand what's really going on for every single clock. So there's no mystery. It's just everything is so clear in front of you. And there are some introduction about the wires. It could be a little bit confusing in the most recent years, since, for example, the terminology wise as well. Since many years ago, when this technology was first invented, it was not named properly, and you can see still a lot of devices are still using MOSI missile. So it's the master L, slave in. So this has been used to all these terminologies for like over 30 years, 30 to 40 years. It's just most recent, like 5 to 10 years, we started banning all these terms. So if you look at the new devices or new sensors, or including the one you are going to develop in your course project probably, we usually don't use these terms anymore. But the thing is, if you work for the defense industry or some other industry are not using the latest chips, they are still purchasing PIC microcontrollers, for example, for their like F-22 fighter jet, for example, right? Or some of the devices are still using still the same code, the same microcontrollers, same peripherals developed 40 years ago. So you need to know what they are, right? So basically, you have a leader. Sometimes it's called a leader. Okay. The leader has 3 names: a leader, controller, and master. So if you see devices in the industry for the 3 names, they are the same thing. Okay. So you can see here it's a M. M is master, but here is labeled as leader. Okay. It's leader, master, or controller. And the counterpart is a follower, a peripheral. Keep in mind, sometimes you see a P, right? P, peripheral, follower, or slave. A lot of times you see the chips are using MOSI and missile. You see all the curves, all these ones are still using missile and MOSI, right? But later on, you'll see other terms like a follower. For example, the code from the textbook, it uses a follower and leader. So you should know what they are. Okay, that's the first thing you need to know. Second, so for the SPI bus, it's synchronized. So why it's called synchronized? That is because you have one individual clock. So the clock is one separate wire. Okay. See, SCK. It's considered as a common sense electrical engineering. Okay, you should definitely know this. If you see SCK, you should immediately know that this is SPI communication. Okay, it's a SPI port. Right, it's a SPI port. There are not too many protocols we need to learn. Okay, during the interview, if they ask you, you told them you have done so many projects, right? And they ask you, like, if you see SCK, is that I2C or SPI? And you don't know, right? You won't get a job. So if you see SCK, it's going to be SPI, right? For the clock in I2C, it's a SCL. It's a clock. Serial clock, CL, not SCK. Chip select. SS is probably a system select or something. Let me grab some water first. Come back real quick. Usually it's CS, not SS. But I think for this diagram using SS, I believe it must be system select. So the second S stands for select. And you can see it's active low. It's active low because whenever it pulls it down to 0, it activates the communication. So that's why it has a bar on the top. It's synchronized because you can have a master out, slave in, or master in, slave out at the same time. You have two wires as a serial ports. So you can do sorry, I should use the follower. I use follower. The follower is able to receive and send at the same time. Keep in mind. Same to the leader. Okay. So there are several different modes, and you can see that there's no certain width for each data, even though it shows you 8 bits over here, but you can define any length you want. Doesn't like UART we learned last week, 2 weeks ago, right? Remember in UART, it's counting for 8. Whenever it reaches the eighth bit, you are either pull it down to finish it, or put a parity bit and then finish it, right? So this one, if you look at the code here really quick, it's the data length, right? It's a variable. It could be any length. And also, this allows for higher speed. So in that case, larger technologies is probably not a good fit for this communication, because larger nodes, larger transistors cannot run fast enough. So usually this is running at 1 megahertz, 1 megabits per second, but it can run it even faster. You can see we can easily run it at 2 megabits per second in the example. And our IPGA boards all these transistors in the IPGA are fabricated in 22 nanometer technology, or 28, I forgot, 20 something nanometers. It's a pretty modern node or technology. It's running really fast. So that is why the main frequency of the board is running at 100 megahertz, right? It's really fast. Compared to the Arduino chips are fabricated in the 350 nanometer technology, and they can only run at 16 megahertz, right? So the 16 megahertz for the microcontroller you have used. And the protocol is really simple, okay? It's basically you have a clock, you have a main clock, and every time you receive a clock, it shifts a bit to the bus. That's it for the leader. And for the follower, whenever it sees the clock, it just takes that data in, right? Very simple. Okay? And there are four modes. So these are labeled as CPOL or and CHPA. However, if you look at the Verilog code, we don't really have these two registers. We define the mode based on the clock or the sensitive list. So let's get into the details of the modes really quick. So this one actually defines at which. So these are clocks. This is ICK, right? So these are the clocks. This is the system select. So whenever it pulls down, it starts the communication. No problem on that. And these are the data, either from the missile line or MOSI line. Doesn't matter. But depending on which mode is being selected, it's either the phase. It's a C channel PA. PA means phase here. I think there's a typo here. It should be CPHA. I'm pretty sure this is a typo from the textbook. So this is a CPHA, is the phase, and it's the polarity So this one defines so CPOL defines the polarity of the clock. The polarity of the clock when, wait, I think I have this written down somewhere. I gave someone the version with the solutions, probably. Did I? Is that you? You? No. Who has solutions? No? Let's see what I have. See what I have over here. Yeah, that's right. So see the descriptions over here. So see, let's see what's the polarity of the clock defines, right? I remember it defines the polarity of the clock when the clock is idle, right? So if the polarity of the clock is 0, you can see during this period, clock is 0, so it's defined as idle, right? So the communication starts from 0, okay? And for the other one, the clock's defined as idle when the clock is 1. So that's the difference. And the phase here, against the typo, CPHA, defines the phase when the data is being taken in to the register of the receiver. Okay, so basically the data, you can see every time it's being taken in, it has to be in the middle. So the edge has to happen in the middle of the data, so it's getting the most reliable data sample, right? So if we, for example, if we choose 0, 0, for example, you can see there's a table. It's a bit confusing. The table is a little bit confusing. I don't really like the table a lot. So, but let's come back and look at this one. If the polarity is 0 and the phase selection is also 0, the falling edge of the clock will put the data available on the line, on the data line, and the rising edge of the clock will, the receiver will take it into the register. How could you tell? So again, we are looking at 0, 0 case, okay? For, you can see these two columns, polarity and phase, right? So we are picking up a code for the mode. There are 4 different modes. These are 2 bits. So we are picking up the 0 mode, or mode 0, which is 0, 0 for both bits, okay? Now the first line of the clock and and the first part of the phase here is being selected. So if you look at the pattern here, what's happening? If you look at this falling edge, let me zoom in a little bit. Falling edge, at the falling edge, it's during the data transition. It's not in the middle of the data. Okay? So that means it's not sampling. But what you can do is let the leader to just drop the data to the line. But the receiver is not taking it in. You can see here's the leader, here's the follower, right? During the falling edge of the clock, the leader will drop the data to the line, to the data line, because clock and data, they are in different lines, different data lines, or different wires. Okay, so the falling edge, the data will be available on the line. And then the rising edge of the clock, the receiver or the follower will take data in. So by that time, that rising edge should be in the middle of the data or should be at the edge of the data? In the middle. Why? Because that's the D flip-flop, right? It's the rising edge. It's edge trigger D flip-flop. The data should be right in the middle, so it's the most reliable data source. That's the way you find out which mode is and how that mode is operating. It's pretty simple actually. Okay, so we want to look at which mode you are selecting, and then you program your Verilog accordingly. Now let's take a look at the Verilog. Don't worry about the nitty-gritties of the code. Okay, we're only looking at the big picture. It's really simple, really simple. And we are looking at, hey, this register is this long, this is this long. I don't really care. There's just the one main big picture. We just need to look at it, look at the big picture. So you can see, first, we know that the data length is customizable, right? We can change the length. Now I put an A here. If I change it to 10, 11, 12, doesn't really matter. It's just changing the vector's size. And you can see this is follower receiver. No, I'm picking up.
This should be the leader, right?
It's the leader. Yes, this is the leader transmitter, and the second one is the follower receiver. So now it's doing the data transmission from the leader to the follower, right? So leader transmitter to the follower receiver. Could the leader be a receiver?
No.
Yeah, missile, right? Missile. Remember?
Yeah.
It's bidirectional. Could the leader be the receiver? Yes. See, the leader is receiving. It's a missile. Okay? But now we are programming the digital block for the leader as a transmitter, okay? And the follower as a receiver. So these are individual digital blocks. Individual digital blocks. So this is now the leader transmitter. Don't worry about the busy, the idle, all these kind of ready flags, the stays. It doesn't really matter. But the main big picture here is, first we need to define the clock. No, let's say first we need to define the data length. We already did it, okay? And second, we need to define the clock. So the thing is, doesn't matter the leader is receiving or sending. It's the leader's role to define the clock. Keep in mind. That's how you can figure out which one is the leader, which one is the follower. How many clock lines do you have for the whole system? How many clock lines?
That's okay.
Only one clock, just one wire. Okay, I've learned circuit one, just one voltage node, just one wire. So synchronized, right? Follower and leader are synchronized. The clock rising edge will be a clock rising edge for both. Same as negative edge as well. So the leader is generating that clock. So the leader is in charge of defining the speed of the transmission, right? There's no other clock available, right? So the communications clock unit, the only or the sole clock source is whatever the clock is generated by the leader. And you can see that if we need a 2 megahertz communication speed, then you need to divide the clock in a certain way. Since we know that we have a 100 megahertz clock, which is available as a reference, and the target is a 2 megahertz clock, and we make a division, we get a 50, right? And the thing is, for 50, we have to count to 25 to toggle it, because count to 25 will toggle it just half of the period. Eventually, if we need a 50 times clock division, we need to count it to 25 and toggle it. It's just very common method in Verilog, okay? Like 25 toggle. So eventually, for the 50 times division, eventually have to count by 25 twice. to form 50. So in that case, in order to generate the 2 megahertz clock, we are counting to 25 by using that 100 megahertz clock. Definitely need to clear the clock every time it reaches 25 and then toggle clock. So the ICK is going to be the clock, and it's being toggled every 25 counts for the 100 megahertz clock. So that part is the clock generation for ICK. Okay, and there should be SS. You can see SS was assigned to 1, and there are only 4 lines, right, for SPI. Keep in mind, it could be an interview question for SPI. SPI is a really common communication protocol, and people like to use it because it's fast, especially for SD card reading and writing. It's pretty much the only way to do it, which is SPI, right? You can run it at like 3 megahertz or something, and writing blocks and pages to SD cards. Usually 512 bytes per page. Have you worked with SD card in the past a little bit? Okay, a lot of details about SD card could be on the interview questions. Remember that, like the page, the size of the page, the block and speed, and a lot of things like all the signal processing techniques like a double buffering, and all these details are pretty important. Okay. So SS was 1, right? So it must be waiting for a pulling down event. So you can see whenever it got started, it pulls it down to 0 first, because it has to enable the chip selection, or SS is probably system selection, whatever. Okay. So pulls it down to 0. And because this is a leader transmitter, right? So which data line we are using, which pin we are using for leader transmitter, according to the just old terms over here, according to this diagram, which one we are using. Mm-hmm.
Because we're sending.
Mm-hmm.
We're receiving, we use these, but since we're sending, it's the
It's mastered out, right?
Yeah.
Okay, cool. So we are doing that line. So for all the 4 lines, we're only using 3 of them, right? For the leaders transmitter. So we are the leader is manipulating that clock. Also, it's pulling this down and pulling it up, and also it's sending data through this line. So there are 3 lines being used. So we have to program the details about the voltage in those 3 lines in a certain timing. So you can see that it's always at a negative edge of the clock. Okay. So the clock you can have 2 parallel always blocks. You can have as many as you can, because whenever you implement it to the digital hardware, they are being implemented in parallel at the same time. So they are all just hardware. Whenever clock comes, they just do their own jobs. Okay. So for the clock divider, when the positive edge of the clock, when it arrives, it makes the division and generate a 2 megahertz clock for you, no problem. And for the second block, it's trying to sense the negative edge of the generated 2 megahertz clock. Why is that? Because it's trying to follow one of the 4 modes, right? We'll take a look at it, which ones this guy's following, right? So at the negative edge of the clock, the first negative edge is able to do something. So it has to change switching between all the states, right? So the first negative edge arrives, it was probably still in ready, right? In the ready state, and it's trying to wait for that send. It's like it's a flag, right? It's a command. Whenever this one, the send signal is 1, the flag is on, it changes the state to start, and it's waiting for the next negative edge of the ICK. It has to wait for another. Okay, keep in mind. When the next arrives, it detects the start state, directly enters this state, right? And you can see this is put down to 0, and directly place that data in this vector onto the line. That simple. Okay? When it's allowed to send the data, it directly places the data to the MOSI line. That's it. All right? And it waits until the next native edge and try to see if all the bits in that vector has been placed on the data line already, to see if it wants to stop it or not. Whenever it's done, just pull the system selection pin up to 1 again and jump back to the ready state. It's really simple. It's basically, if you get rid of all these redundant ones, right, like preparation, ending, and all these kind of things, it's basically just the main picture is just whenever it's ready to send, and it sends. Okay? Native edge, keep in mind, native edge will put the data on the data line. Another term is the data will be available. But is the receiver receiving it or not? The data, there's only one data line, right? MOSI, right? So MOSI, the master or the leader is sending, and the follower will be able to see that voltage. It's just one line. But doesn't necessarily that the follower is taking it in. Why? It's like you are feeding me for something, but I don't open my mouth, right? Like, nothing can get in, even though this is available here, right? Right. So what is making that available is you have to wait for a rising edge of the clock, right? Even though the data is over there, it's touching it, it's sensing it, it sees it, but the thing is not taking it in. So we have to look at this follower receiver here. Follower receiver here. So you have to define the data length to store the data, right? Bit by bit. Again, don't worry about the nitty-gritties about this. Nobody is gonna memorize it. I don't believe anyone will interview you about just memorize the SPI code or I2C code. It's impossible. Even NVIDIA is probably not going to test you on this. It's just all of them are IPs are available to use, right? You can see it's the positive edge of the clock. So the question is, do you need to generate the clock by the follower?
No, it's receiving.
It's receiving, right? It's the same data line. It's just receiving. You can see it doesn't need to create another block for generating clock. It's just directly sensing it. It's the positive edge of the clock. And so whenever it sees that one is getting put down to 0, this is also from the leader, right? So from the leader. Both signals are from the leader. See? Whenever it sees this comes in and this is put down, and just take it in. Really simple. For the follower, really simple. Just take it in. And take it in and shift the index, right? And move to the next stage and shift the index to keep doing this. Probably some of them are not. Why do they have to separate the two states? It's probably because in the ready state they have to use the if statement to check the state of the SS. Does that make sense?
Yeah.
Yeah. Again, we don't really worry about the nitty-gritties about that. Sometimes if you modify some of the flags, it's still gonna work. So it doesn't really matter. But it's being organized in this way, and eventually I just take one bit by one bit, and eventually whenever it reaches the max of the index, it stops. Okay, so that's for the follower receiver. and there's a pair of code for follower transmitter and leader receiver. So the difference is the leader receiver, even though it's a leader, it's a receiver, but still need to generate the clock signal. Okay, even though it's receiving. And same for the SS, I believe. No, so you can see here. So the SS is now controlled by the transmitter, even though it's a follower, but it's controlled by the transmitter. Okay, so now let's come back to look at this one. So it's basically negative edge will place the data to the line, and rising edge will take it in, right? So it's basically doing this and this. Is, I think it's 0, 0, 0, 0. It's a mode 0, 0. But we don't really care about that for here. We don't even need to have a flag to define the mode. So this happens when you are using a microcontroller. You're looking at the registers. You probably need to write a register value over there to define the SPI's mode. So in that case, the mode can be changed for that digital device, right? But now I don't think we can change it here, right? Because all these are already defined. It's the negative edge, put the data available on the line, and positive edge to take it in, right? Okay. And there will be a sensor to let you guys to use. It's a digital sensor designed by Xilinx and Digilent, the same company. So you can directly plug it in to these GPLs and use the modules available from the textbook to do it. It's reading optical signals. It's a photodiode, reads the optical signal, converts it to digital signal in a SPI mode. And eventually, it's able to communicate directly with your SPI modules available from the textbook. And the light intensity values are read as both binary values can displayed on the LED. So the LED is showing the binary number of the 8-bit light intensity from the sensor, and also it's being displayed on the 7-segment display as well. So you can see the maximum value is probably 255. So you'll know that it's an 8-bit sensor, right? So I was using a flashlight, so when you turn on the flashlight, it directly saturate the sensor. So it's a really simple experiment. So I can expect this can be done within a week or less than a week, because I'm not asking you guys to invent anything. It's just basically plug it in and repeat it. Yeah. Okay, so the main box is a project, course project. So first, what we are making it's an oximeter. Okay, it's different from the ones we did in microcontrollers a few years ago. So we are making a digital sensor directly, and it's a research project, which means you need to do a literature study. I know everyone hates it, but that's a process that you guys learn what other people have done in the past. It's really short, only 5 pages, and you are allowed to form a team of 2 to 3 people on the team, and there are tasks. For example, the literature study, preamplification, ADC, SPI, and a digital interface. So I have examples for you guys. For example, for the preamplification, Here, section A. I have done this many years ago in my analog lab. We just built everything from a robot IR sensor. It's a line trackers IR sensor, but it's the same IR, right? Infrared. It's emitting an IR signal and shoots through a finger, blood vessels, and the blood vessels, the red blood cells absorb the IR light depending on the amount of red blood cells in your blood vessel at the fingertip. And then the reflection carries a varying amount of IR light, and which shows heartbeat frequency, okay, depending on the oxygen level or amount of red blood cells at your fingertip. So why this is a very good project? Because this is very typical analog signal from the environment. It has an arbitrary DC offset. It's small, and it's analog. So this applies to a lot of different engineering projects. It could be a biomedical signal acquisition. Could be any types of analog signal acquisition in the future. And you guys are making a digital sensor which is a lot different from the ones being used from all these microcontroller projects, because everything will be put into one ASIC, even though it's IPGA ASIC, but it's still ASIC. It could be converted to a digital chip, just one single chip in the future. One single chip is able to digitize in the analog signal from the fingertip, and eventually calculate your heart rate from there. So this could be a portable healthcare device. Okay, it's a low cost and portable healthcare device. So the research topics is mainly on a few things. Keep in mind. A, B, C, D, and E. Okay. It's called blood oxygen saturation ratio or something. Okay. There's a certain way to calculate the SpO2. I think that's a parameter. And how do you calculate it? If you measure the heart rate or the amplitude of the signal, how do you convert it to a biomedical parameter that can be used for healthcare givers, providers? All right, so you need to do some study on that for the physics and the science behind the scene, right? So how this works and why we are using this parameter to measure how your lungs and your respiratory system is functioning. So that's section A. And section B, why do we want to compact oximeters? And what's the advantage of using our system over other commercial ones or the ones available on the market? Do some research. I'm not saying ours is best, right? Just doing some research and compare. It must have pros and cons, right? So some of the portions better than others, and some of them are not as good as others, right? Definitely. So section C, search for some of the available parts from the market, and what are the amplifiers and sensors and microcontrollers are being used. Okay, consider the cost and why they use that specific type of microcontroller, right? And also including amplifiers. So this could be important because you can see there are different types of amplifiers being used. And the one I used here, like this one, it's a very expensive amplifier. It's really high quality, but it's very expensive. So I used two of them, and I purchased this amplifier from TI, and I didn't buy a lot of them, so it's like each one is $20 just for one instrumentation. It's called instrumentation amplifier, high precision. So I got 2 of them. So only amplifiers are they cost like $40. It's ridiculous. And I got another final stage of amplification. So you can see for most of the amplification circuits and filtering circuits, you have to use a high pass filter first, and then you bump the AC signal to its desired DC offset. That's the main thing I want to teach you guys. You know, a lot of people don't know how to do it. So in circuit 1, you guys learned amplifiers, right? Op-amps. But you use the dual suppliers, 15 and negative 15 volts. But in real world, we usually don't have negative 15 volts. It's just trying to let your reference voltage to be 0 volts, because you have a bottom top rail, and in the middle is directly just 0 volts. So you can directly just ground the non-inverting terminal to make it super simple. But in the real world application, you need a DC offset, which is right in the middle of the voltage range, if you are grounding the other terminal, the VSS of the op-amp. Okay? So something you have to know. Very important. So through building this amplifier, learn how to calculate the cutoff frequency, high pass, because heart rate is usually, for example, 50 hertz to 180 hertz probably. It's the normal range. And you can set up the range from like 30 hertz to 200 something range as a signal's frequency. And there's a frequency called from the power supply, from the plug, which is 60 hertz. It's really annoying. I don't even have seen that in the past. So a lot of times, if you don't have any signal being injected into your system, into your oscilloscope, and your probe is not grounded, in that case, you can see a sine wave appears in your oscilloscope, and that is the noise from the plug. It's a 60 hertz from the 110 AC voltage. That's the noise. So a lot of times, for the very tiny signals, we need to get rid of that 60 hertz noise as well. So in one of the filter here, you have to design the 60 hertz removal filter, right, to make it cleaner. I think this is what I did. It's probably one of the components can be replaced, and we don't have all the components available. Sometimes we probably don't have many of these ones, and these are $20 for each, so I don't really recommend it. But you know, if things don't work, we can always come back and use whatever I did since it worked. So we were able to connect it to the Arduinos and display it through the IDE's serial monitor. So this is method 1 for preamplification. All right, and I gave you several options that I found online. I think they must work, since I saw that they posted the results here. And they even have a peak detection circuit whenever the comparator, right? So whenever it passes a certain threshold, it just shows the pulse to make it cleaner. Okay, so this is the original signal, I believe. And here's a schematic. It's really simple. You can see it's very reasonable circuit. I mean, I hope you guys in the future, whenever you see a schematic like this, you know what they are. I think that should be one of the outcomes from this computer engineering program, right? If you guys have the chance to do a project with me, now we do. Everyone should actually, should do a project, at least one project with me before graduate. So let's see. If this is the interview, right? This is very reasonable, right? The interview. Usually they'll give you a schematic. And sometimes they're nicer, they'll give you one day, to study the circuit and explain the circuit to them. I've seen a lot of interviews like this. They give you a circuit and give you 1 day and come back and explain presentation, okay? And also a lot of times they don't even give you the chance. Directly give you the circuit, and whenever it becomes competitive, you directly just tell me what's happening on the circuit, just on site, right? So you guys want to be prepared for either case. So for the first one, what is happening? If you see every component, do you know why they are there? That should be the outcome eventually. You should be able to know, hey, that cap is just a filter. Oh, that cap is just a something. It can be 1 micro, can be 2 micro, can be 10 micro. Okay? This one can be 33K, can be like 50K, doesn't matter. Or it matters. Let's look at the first one. So definitely this is a regular op-amp. LT means what? Linear Technology is the company, right? Who invented LT Spice as well. It's linear technology. They have a lot of LT something op-amps and analog circuits. So what's the circuit over here, though? What is this guy?
It's a light emitting diode.
Hmm?
No, it's the other way. So it's
What is this guy?
it's a photo resistor.
Yeah, it's a photoresistor. It's an IR light receiver, right? It's a IR light detector. It's being reversely biased means, all the photodiodes are reversely biased
Yeah.
when it's connected to the op-amp. So it's converting the current to voltage, right? So the first stage is performing as a TIA, the transimpedance amplifier, because it's converting the photocurrent into a voltage. Why? Because whenever this one generates a current, it pulls current this way. Ignore about the caps first, okay? We're only looking at the DC part of it. So it pulls current that way to ground, from here to ground, right? So in that case, the photocurrent generated by this guy is going to flow through the resistors, and there will form voltage drops. So that voltage drop will appear as a voltage signal as the output of the op-amp. Okay, so that's how you can get voltage signals from the light. So it's a light to voltage converter, right? And the capacitors are doing what? These are filters, right? If you put a filter in parallel with a resistor like this, it's a low-pass filter, and it can calculate the cutoff frequency of this pair. It's a 1/2 pi RC. So you can easily calculate the cutoff frequency of that low-pass filter. Okay, same as this one. It's also a low-pass filter. Why is it low-pass? Because high frequency will directly being shorted by the capacitors to ground. So high frequency will go through the capacitor to ground. So it's getting shorted to ground. So high frequency will be attenuated significantly, but low frequency signal will go through this one and form a drop. So it's not getting attenuated. All right. So now move to here. You got a voltage signal, right? It's a varying voltage signal. Then what's this? What is this part? It's a high pass filter. It's a RC filter. It's a high pass filter. It's a first order passive low pass filter. It's the easiest one. You should know, definitely. Okay. And why you have a 1 volt here instead of ground? That's the DC offside. Okay. Apply superposition. Keep in mind, I have told you guys, I've gone through superposition for multiple times in both classes, right? So superposition, that DC signal will be directly added to the output node. You got an AC swing after high pass filter, the original arbitrary DC signal will be filtered. It will be gone. We don't like it because you don't know what that will be. Different person will give you a different DC offset, and we make it super difficult to predict. So eventually, we use the high pass filter to remove that arbitrary DC offset. Okay, so it's like basically your signal information, right, is oscillating around the arbitrary DC offside, which is bad. We just remove it. So this high pass filter will remove it, and then you add a known, it's 1 volt. So all the AC signal will swing around 1 volt. It's good. I don't know what's the DC, what's the VCC here. It's probably serpent servos. But usually we use 50% of the VCC as a default DC offside. So we always want your signal swing around 50% of the range. Here's your top power rail. Here's the ground, right? So it's basically half of VCC or VDD in the middle. So maybe 1 volt is 50%. If it's a 3-point servos VCC, then it's very close to 50%. So which is good. Okay, I don't know yet, but seems like it is. And then here as well, high pass, and so they added another stage of low pass filter here, trying to further filter out any high frequency signals. Maybe not necessary, but they have it here. I don't know which one they want to filter out, but you can calculate. It's 1/2 pi RC. And another stage of amplification plus low pass filter as well. So there's a DC gain being added to this stage, which is 1 mega over 33K, right? So that's the DC gain. If you don't know how to calculate it, study it. This is a course project. Study it. You can also ask me during office hours. It's really simple. Really simple. Keep in mind, it's just everyone should know it before graduate.
Yeah.
Everyone should know it. Every one of you should know it. Should master it, not just know it. You should be able to build it on the breadboard and implement everything on the breadboard. Okay. And then another stage of low pass filter. Probably they observed some certain frequencies of noise. They want to get rid of it, so they added another low pass filter for some reason. And it's pretty much ready, so the signal is ready here, so that's why they put an output here. This is probably the original signal, shows the heartbeat. And it decided to make a voltage follower. You can see the voltage follower, 0 ohms. It's basically a wire. This is the voltage follower, and I think this is how is a comparator because there's no negative feedback. And eventually, I think this stage and this stage helps the circuit to form the DC spikes, which is not necessary, but they decided to do it. See? It converted the original pulse from the fingertip to these spikes, so it's easier to detect. We don't even need to do that. So if you guys want to follow this guy, let's save some money to not ordering too many components. Why we want to see the spikes, right? It's actually a really simple circuit. Done. 1-2 stages. So what's the overall voltage gain? Voltage gain. I'm asking for voltage gain. Just stop right here. Voltage gain. DC voltage gain is only 1 mega divided by 33K. And this is not a voltage amplifier. This is a TIA. It's a current to voltage converter. So the gain of this TIA is 1 mega. Because the current, whatever current will time 1 mega to form a voltage. So that's why it's the voltage divided by current gain. So it's the gain here is 1 mega. All right. So for this project, you guys will. I think that's task 2, I guess. Right. Design a per-amplification circuit and display the signals on the oscilloscope. You have that sensor. You got an amplifier on the board, and you put your finger on the top and display that signal on the oscilloscope. Okay, at the same time, another member of the team should implement that ADC circuit and SPI on the IPGA and display results from a potentiometer analog input in an Arduino serial monitor. So what does that mean? Because the preamplification part of the work is totally different from the section 3 of the task 3. So they should work on the two different tasks at the same time to save your time. So XADC, I followed this tutorial a few weeks ago. I just did whatever I showed you here. It has a project ready posted to their website. You follow that, follow this diagram connections, and you will be able to show the ADC results on the 7-second display easily in probably like 20 minutes. So, but you have to interface the ADC inside the IPGA with the SPI digital module. So this was a course project from last year, and I was looking at some of the presentations from last year. I found out these two are probably helpful. You can look at Taylor's. She has everything available. I don't mind if you want to copy all the code. And you can see she had a potentiometer as analog input. So we are going to use our oximeter's analog signal as to replace the potentiometer's voltage input, right? But she didn't work on the per application since that was not part of the project. So she just used the potentiometer to change the voltage, analog voltage, and it's being digitized by the IPGA and shows the digitized result on the LEDs and also in the serial monitor of the Arduino. So why the Arduino is able to display it? It's because the SPI, right? Arduinos have SPIs. So IPGA, right? IPGA got an ADC inside. ADC internally has all the digital output inside the chip, and your SPI receive the chip in parallel, or receive the data in parallel, and convert it in serial signal through the SPI's output. And that one interface with Arduino, and Arduino has already built-in SPI ports, so it's able to take it in and hand it to the UART port for serial monitors display. So another thing you guys will learn is the IPGA is the 3.3 volts device, and the Arduino is the 5 volts device. And SPI communication is bidirectional. So eventually, the basic 3 board is gonna receive 5 volts logic, which is gonna damage it immediately. So you have to use a voltage shifter. It's a level shifter. That's converting all the digital signal from 3.3 volts to 5 volts and to 5 volts to 3.3 volts. So you need a little level shifter in the middle. It's really practical, okay? So when you guys are working on senior SEM projects, you will probably see this a lot. It provides a lot of solutions to you guys. And there's one example. I got a second example from Ian. I think his worked as well, but in a different way. So just two references. I don't mind if you copied everything. Just make it work, right? And number four is I want to plot the heart rate signal, the oximeter signal in real time in Arduino's serial monitor. So what that means is you want to display this eventually. I mean, you are able to show the data points in serial monitor. You should be able to plot it in the serial monitor as well. It's just a serial plot instead of serial monitor, right? Just one different option in the drop-down menu. And the presentation. So there's no final exams. This is the final project. It's a final presentation. Now let's see. Is it taking 20%, right?
I think so.
Is it 20%?
So?
So I have the 4 tasks with different deadlines. Since I know you guys, okay. have to split the deadlines in 4 different ones. Otherwise, you won't start it until April 15th. First task's deadline is when April 1st. Is that just next week?
It's next Tuesday.
Next Tuesday, so it's a week from now, right? So we do have a SPI, we do have several tasks, right? But the thing is, it's just adding a little bit more tasks to you guys for this coming week. So the workload can be a little bit high, but the thing is, I don't think I plan on giving a lecture on Thursday. So I already did this today, so I'm not doing anything on Thursday. So I will be here and you can come here as well. Let's just get something done. So that's critical. Why? Because we need to get the parts ordered. Okay, and that is why Ford's College is so awesome, because we only have 14 students. I'm able to order customized parts for every single one of you. So you form a team, you got a parts list in a spreadsheet. I will be able to. Oh, let's do that. So you put the parts in DigiKey or Amazon. Don't have 10 different websites, right? I have to check out for 10 times. So just either use everything on DigiKey or Amazon, or maybe at most for 2 sites. Some of them are from Amazon, some are from DigiKey. Doesn't matter, okay? So put in cards, and I will just come to you and check it out on your computer. All right? So it's not a lot of work actually. 14 people. It's only like 3 or 4 teams, probably 4 teams maybe. Yeah, I did 100. So 100 in embedded systems, 100 students, 50 projects at school. So came back and seeing 14 students is a treat. Yeah. And I think it's different. It's a different outcome, right? Yeah. And also I find out one interesting difference is, if you have 100 students in the class, they are allowed to cheat. Allowed, not really allowed, but allowed to cheat. You can tell like 80% of the students actually cheated through all the whole 4 years, because they can hide behind other people and join a stronger team and not really doing anything. So eventually not getting picked up by the professor. It's very common. They graduate without knowing all the critical stuff. It's very common. But for 14 students, you got to know everything in order to graduate. Since I know you so well. Let's see. Okay. Any question on this? First week. Let's be clear. Deliverables. Task 1. Literature review. How many pages? 5. How many references? About 10, I guess. Oh, 10 references. So where do you find the references? I already provided you with a lot of references. You can see these ones. It's already 5. Okay, you can search for these research articles, right? It's like a conference paper, even though it's not a really top conference or journal. But you can see, if you look at the circuit, after seeing a lot of circuits like this, it's just so familiar, right? You got one amplifier, one high-pass filter, and it's same thing. Come back. It's microchips, design, advice, examples. You can look at their published schematic. It's making things so simple, right? It's already there. Just get the parts ordered. So that could be a very good experience to figure out which parts are necessary, which are not. We see the schematic, but definitely not everything should be ordered. Okay? So whenever you are ready to order, I will look at your schematic and I'll give you some feedback. So that will be a really good learning experience for you guys to know what are necessary to build a preamplification circuit for ADC. So so when the parts are due, the parts, append the list of electronic parts and schematic, have all the parts in the cart. So when we are going to order the parts, let's see. I think that was next Thursday. Yeah, so that will be Tuesday next week, right?
Yeah.
Okay. So yeah, so form teams and make sure you guys will start doing the literature study, writing that 5-page stuff, study the preamplification circuit, write the reviews, adding the references, and putting the parts in the cart. After doing the review, you will be able to see, just comparing the schematics. You can see this guy uses high pass, low pass, 2 stages. This guy uses low pass, high pass, 3 stages. And after the comparison, you will find out this is probably the best way to do it. And then you just put the parts in the cart and make it ready next Tuesday. So we'll get things ordered on Tuesday. And usually it takes a week, right? It takes a week. And next Thursday, I will be able to find a space for you guys in the electronics lab to let you guys build the amplification circuit. But we probably don't have the parts yet, right? So in that case, probably should focus on the ADC part on Thursday next week. So you can start working on the SPI, the ADC, or the tasks that are not finished from like the SPI's tutorial, or maybe the lab, the Pico Blaze whatever lab later this afternoon. So you can work on these 2 tasks. I can probably postpone that deadline for the lab a little bit. I'll look into that really quick. Okay, just put everything in 1 week is a little bit not realistic. And the week after, we'll be basically working the lab. Even though I don't have formal lectures, but you guys should come, okay? Because we do have firm deadlines, so I believe it should work. Okay, so if you don't come and work on it, when are we going to finish it? Right? We have deadlines every single week, pretty much. Okay, so I believe that should work. So I'll be here, or you. Let me see. Should we come to the class, or for the ADCs? I think I will be just in my office probably. So if you work in the class, you can find me over there. If you work in the lab in 602, I'll give you access to 602 probably, and also I'll let you guys go to the electronics lab to work on the project as well. Okay. And there might be another quiz regarding engineering ethics. Definitely don't worry about that. I'm not going to give you very lengthy ethics lectures. It will be just a quiz. You read a PDF and finish the quiz. Like 20 questions, then you're done. Okay, so we check the box for number 4 outcome on ABAT. Yeah. That's everything about the rest of the semester. We don't even have another lab. There's just one more lab this afternoon. And for the rest of the semester, just on the course project. You have a lot of time in the lectures, during the lectures, and also a lot of time during the labs. Okay? We will build a system. Any questions on anything? How many weeks left? Is that 4? Including this week, 1, 2, 3, 4, 5.
Yeah.
Yeah, 5 weeks. A lot of time.
So I guess for the parts list, do you just want us to give you like the DigiKey card, like share it with you?
Can you share?
Yeah, you can share the DigiKey.
If you can share, that works too. Yeah, I can. Yeah, if that works. Yeah, whenever it's necessary, we'll probably have a few lectures on the ADC or anything. But I don't think that's necessary for now. But we'll just to work on projects. Okay. So you can turn in that in-class exercise for the 0.9 points. Something.
Yeah, everything counts, I guess.
Yeah. It could make a difference sometimes from A- to A, right?